This lesson deals with supplemental problem 10.3. You can find this problem in the ECE202 ebook in the Chapter 10 Supplemental Problems starting on page 5. Let's again take an example from ECE201. This is supplemental problem 7.5, which consisted of a battery, 2 resistors, an inductor, and a single-pole, single-throw switch. That's going to close at t equals 0 and short that resistor out. Let's solve for the current I of t, but this time using the Laplace transform. We'll use our 5-step algorithm. So the first one is to find the initial condition of the reactive components, and here's just the inductance. This switch has been open for a long time. We have a DC input. We can treat our inductor like a short circuit. In other words, V is equal to L di dt. If the current's not changing, then the derivative is 0, and the voltage then would be 0 times the inductance, or 0. So if this is a short circuit, I've got 16 volts here, and I got 4K and 4K. So the current would be 16 divided by 8K. 16 divided by 8 is 2, and 1 over 1K is milli, so it's 2 milliamps. The second step is to transform this into the S domain. And so the switch is going to be closed, going to short this resistor out, and then we're going to have a voltage applied to our circuit of 16 volts. That'll be our step function. And then our inductance will be replaced by SL in parallel with a current source whose value is a step of 2 milliamps. So let's take a look at that. Our next step is to perform the S domain analysis. So let's simplify this circuit. Anything in parallel with a short circuit is just 0. 0 times 4K over 0 plus 4K is equal to 0, so let's replace that by a short circuit. And then let's make this a one-loop circuit. I'm going to do a source transformation on this. I have a voltage source with the plus sign where the arrowhead was pointing, and then the minus, and then I got a series inductance of S times L, and then the value of the voltage would be the product of these two. So the S's cancel, and the 2 times the 0.5 gives me 1, and then I have a milli multiplying that. And that will solve for the current I in the S domain. We could solve for I by taking the voltage across this series impedance and divide it by the impedance. This node voltage here is 16 over S, and this node voltage is a minus 1 milli, so it's a minus 1 milli. And then the total impedance is going to be 0.5 S plus 4K. Let's multiply numerator and denominator by S, so I'll get the S is canceling here, so I've got 16, and I've got a plus 1 milli times S, and likewise multiplying this by S, let's leave this in front here. Pull out the 0.5, and so 4K divided by a half would be 8K. The half out in front, reciprocal, will become 2, so I have 2 milli times S plus 32. Step 4 is to perform a partial fraction expansion, and I can do that because the highest power of the numerator is 1 for S, and the highest power for the denominator of S is equal to 2. I could write I as some K1 over S plus some K2 over S plus 8K. Then we'll multiply this by S to find K1 and let S equal 0. Terms cancel, and so I have 2 milli times 0 plus 32 over 0 plus 8K. And that's going to be equal to 4 divided by 1K. Reciprocal becomes milli. Likewise for K2, we'll multiply by S plus 8K and let S equal minus 8K. Terms cancel. And then I have 2 milli times minus 8K plus 32 divided by minus 8K. This becomes minus 16 plus 32 is plus 16 divided by minus 8 is minus 2, and 1 over 1K is 1 milli. My last step then is to find the inverse Laplace transform. So we have that I is equal to K1 over S plus K2 over S plus 8K. This is our step function, so it has a strength of 4 milli times U of t. Constant here is minus 2 milli, and 1 over S plus alpha is e to the minus alpha t, so e to the minus 8k times t. Again, let's write this as a time constant, so 1 over 8k is 125 microseconds. Pull out the U of t, and I got 4 milli, minus 2 milli, e to the minus t over tau. Tau is 125 microseconds, and all that times U of t, and the units are amps. And this is supplemental problem 10.3.